I will now start today the last lecture when we will discuss about the plasma physics. Please note the question will be handled today through by Professor Asim Paranjpe. So halfway through the lecture, please type in your questions directly to him. And towards the end, if there are any questions, we will look at them. So I also want to just say that there are few images that are shown in these lectures. For example, these are freely picked from Google Images and are essentially in the same spirit as these equations are essentially taken from various books for illustrative and discussion purposes. So, so the topic today will be plasma physics, and let me just share full screen. I hope you can see my full screen now. And,
Yes, Nishant, go ahead.
Thanks. So, so this is basically a subject which is somewhat more involved than the usual fluid dynamics. Um, and many textbooks or various speakers, when they start speaking about this subject, and if you yourself have ever looked at a couple of textbooks, you might have seen this subject starts with TV ad like sentence, like 99% of universe is made up of plasma. So this is more of a yeah, what I would say a TV ad like sentence. So that apparently is motivation that one must look into the plasma, given much of the matter in the universe is in this state, okay, which is much of the baryonic matter in this is in this plasma state. Luckily, not on the Earth, but most of these stars, galaxies, uh, the uh, the medium is abundantly in the plasma state. So, what really is plasma, and what it all can drive uh, in a macroscopic perspective? One has always wondered about the existence of magnetic fields at various scales, and as I will come to defining plasma in a moment, uh, you already know that this is a medium which can conduct electricity. And as you also know that a medium that can have an electricity can drive magnetic fields. And in a macroscopic description, basically these fields that are produced are influencing these particles, the plasma particles, while the same plasma particles are also responsible for the generation of these magnetic fields. It's a tightly coupled system, unlike the what you might have also learned in terms of plasma orbit theory, where one tends to study the charged particles under the influence of externally applied electromagnetic fields. So there are two somewhat different approaches to study the plasma. But before that, you just look at these pictures where you see that magnetic fields are essentially observed over all the scales that you can observe. So in a lab, you have a magnet. If you go to the Earth scale quickly, you go to 10,000 kilometer scale, you have a magnetic field for the Earth. These are the aurorae that are basically when the charged particles through the solar wind, they hit the Earth's magnetic field towards the pole, north and south pole. You see this beautiful sky. You look at the sun. The sun has a diameter of about 1,400 megameter, and it goes through a cyclic activity from large magnetic activity to the small magnetic activity, comes back. Essentially, the point is that it also supports a magnetic field on the scale of the size of the sun. on the order of 1000 megameter. You can zoom in and you find there some very intense magnetic structure called the sunspots. A single sunspot can be bigger than the entire Earth. The order of, say, Earth is like only in this scale, say 12 megameter, around 12.8 megameter. So you go and observe magnetic fields in different parts of the universe. You always find magnetic field, that there is something. And you look at sun and Earth. This is also tightly coupled. This entire interplanetary space is filled with magnetic field. The scale of this magnetic field is now 1 astronomical unit. You go to the entire galaxy. The whole galaxy is filled with magnetic field. Okay. It's like 10 kiloparsec scale. So these are uniform large-scale magnetic fields. Basically, the magnetic fields occur within the system. They are distributed over whole range of scale within each system. You can go even to the galaxy clusters, you still find magnetic fields. So the point is, the whole universe is not only filled with plasma, it also filled with magnetic fields. Perhaps not such a surprise, because the plasma does drive electric current. But the surprising part is that whenever you drive an electricity through a wire, you know that the current will be dissipated through the resistance in the wire. One can work out, and today we will look at how to work out. But we can work out, if given a resistance of the wire in the wire, how long it will take for a magnetic field to completely dissipate away. Given the age of the universe is so large, it is also a valid question to ask, even if there was a magnetic field, wouldn't it have decayed over the lifetime of the universe? So the answer is, it might have, unless supported through various motions in plasma. And that would be the topic as dynamo. So given this is a single talk on plasma, I will very quickly try to give you a short summary of the motivation involved and how does one really study these systems. And later on, perhaps in lectures by Dipanjan, you might hear how these equations are then put together in a computer, and some interesting astrophysical subject can be studied and pursued. Okay. But the goal of these lectures will be to derive basic equations and to give you a rough idea of what are some conserved quantities and what might be the underlying microscopic processes leading to the dissipations. So these will be the goal today. So let us define plasma. For a macroscopic purposes, you can again think in terms of, like I defined the fluid element before, you can now consider a plasma element. But let's go a step back and start from a neutral gas. What happens if you start heating the gas? People also call it a fourth state of matter: solid, liquid, gas, and now plasma. Yeah. So when you take a piece of metal or something, you take any low temperature object, you start heating up. Yeah, it will go into perhaps through liquid state to the gaseous state, and then if you keep heating the medium, you might end up getting a medium which is simply a mixture of ions and electrons, because now that you have heated it so much that electron will no more remain in the with the nucleus, and then these will be knocked out of the atoms. And one important equation to look at is the Saha ionization equation. You can read more about this. I'll just briefly sketch that the number density of ions divided by the number density of neutrals takes this proportionality. This is I've not in most of these parts I've only emphasized the dependencies. So you see that it is directly proportional to the temperature, to the 3.5 power, and it is inversely proportional to the ion number density. That's somewhat less obvious a fact, but it is true that if you have more number of ions, you have also more number of electrons. So if that also increases, then the probability of recombination will also increase. Okay. So just by intuition, you know that ion number densities must increase as you increase the temperature. You can try to draw this function exponential of minus ui by kBt. Draw this function as a function of temperature. You'll find that this function basically goes from 0 and then saturates at around 1. Yeah. So it's a function which looks like, I'm drawing a cursor here. Okay. Draw function e to minus 1 by x. So, and ui is your ionization potential. Okay. So only when the temperatures are large enough, then you start to have enough number of ions. Even if you have a, by and large, a neutral medium and only a very fraction of a percent in terms of ions, that medium is sufficiently good to conduct electricity. You know that once you have ions and electrons, they can just be moved, and as soon as the ions and electrons are put into motion, they will drive currents. These currents can in turn produce a magnetic field simply by these motions. So if something is supporting the motion, one can imagine that the currents and magnetic fields might be also supported through those motions. This will be at this level a general enough description that you have a mixture of ions and electrons, and we are not putting any constraint on their number density or their separation. And one can take whatever approach one wants. Again, you can track individual plasma charged particle, and one can write down the or study the dynamics under the influence of electromagnetic fields. Okay. But that will not be the approach. Of course, again, the same difficulty arises that you have so many number of particles, so many number of that that description may not be a viable one. But there are in plasma often a situation that you don't have actually any choice. It does not necessarily offer the macroscopic description, and then one must go to either kinetic theory or even a particle picture. And that's, of course, more accurate if one could handle and do that. But luckily, for most of the plasmas of interest in space, it turns out that much of the plasma is not only it's possible to deal with them in terms of fluid picture. These are also non-relativistic. They are not moving close to the speed of light, at least for most parts of the universe. So these are non-relativistic mixed plasma state, which can be described by a single fluid. By single fluid, one simply means that the ions and electrons are so much mixed up that if you take the smallest plasma element, like a fluid element, by that one means that you don't resolve any scale smaller than that scale. So that small plasma element will be on an average charge neutral. Okay. On an average, because one can create a spark or create an electricity somewhere which will create a charge imbalance, but that charge imbalance will be quickly shorted out due to high conductivity of the plasma. Plasma necessarily have a high conductivity. So those will be shorted out, and therefore the charge imbalance will be will die out. How that happens? So imagine that you have a plus concentration plus here and minus here. If you create a charge separation between plus and minus, I won't have time to derive all these equations, but it's a simple equations, and I'll sketch again somewhat later. So if there is plus here, minus here, what will happen? They will have electric field between the two. Plus will attract the negative. Medium will have a conductivity which is large, and time scale of shorting out this electricity is basically very short, because that goes as 1 over sigma, or 1 over conductivity. So because sigma is large, the time scale to short out the electric field becomes very, very short. Okay? And I'll come to the numbers in astrophysical context, that these are very, very short. And that's why it is known, or one can call this a quasi-neutral mixture. quasi-neutral because when you go to some small element, this is always in a neutral state. There are as many positive charges as there are negative ones in a small plasma element. So that's why it's nearly neutral as far as um, that plasma element is concerned. It is still very peculiar because you can imagine that there are adjacent plasma elements you can just put together. Suppose the plus charges, the ions are somewhat heavier or they are much heavier than the electrons. So suppose they are fixed. So what happens that the electrons can slide past ions while maintaining the charge neutrality. So one could have a situation when the charge density, the net charge density is zero, but the net current density is finite. Okay, so this is a very peculiar, and I urge you to imagine about it, how it is possible. But it is simply that the plus and minus can move in different directions. You can take 1D motion, the plus is going towards plus x, electrons are going towards minus x, joint motion is giving you a current towards plus x, and any small element need not have any charge imbalance. Okay, so while you have a finite current. Okay, so it's a quasi-neutral mixture, and that will exhibit a collective behavior. What does it mean by a collective behavior? Collective behavior in this sense can be understood is that a single particle, for example, if you look at the galaxy as a whole, a single particle will have its own magnetic field at its own scale, and you might try to look at how that picture will look. But if in a macroscopic sense, so many different electrons and ions are put in motion, the entire response of this system appears to be due to a collective response from all these individual charged particles. So what you image as a galactic magnetic field, it appears to be a collective response due to various different species in the plasma. Okay. So it exhibits a collective behavior. Okay. After all, there is a big difference between the interaction here. In fluid, when two neutral molecules needed to interact, we wanted them to interact because the whole criteria for defining fluid was collisions. So two particles can collide, but only by essentially touching each other, right? In this case, the electromagnetic fields, or suppose the electric field, in this case, suppose you have a plus one place. So the electric field due to a charge is a long range force. Okay, so it can influence the plasma particles not only in its vicinity, but throughout the plasma, right? It's 1 over r type, 1 over r square type electric field. So it's a long range force basically, right? So if you have one charge imbalance somewhere in the plasma, it can essentially affect the entire plasma all the way up to infinity. So in that sense, the interaction properties are very different from the neutral medium. Okay. But is that really so, that the force is really so large scale? We also know that given that the plus and minus charges are not like in a solid, they are in a plasma state which can move. As soon as you have a charge imbalance, they will try to move and try to short out the electric field. They will screen the charges, right, naturally. So if I suppose I haven't drawn it here, but all of you might have seen or can look up the Debye shielding. It's like if I have a plus charge here and freely floating electrons in space, what will happen that many of these electrons will feel the electric field due to this plus charge and come and surround this plus charge. So to a distant observer, it might be so that the electric field due to this collection of charges is essentially zero, because the entire cloud is shielding the positive charge. The electron cloud is shielding the positive charge. And one can determine what is that distance, and you can work out is known as Debye length. It's a measure of shielding distance, and it goes as temperature divided by electron number density to the half. Okay. So one of the critical criteria for our space plasmas or for fluid description is that this lambda d must be very, very small. Okay. It must be very small compared to the system size, such that the smallest element we are not able to identify between plus and minus separately. For us, this is a single fluid. It's so mixed up. Okay. But in order to have an efficient shielding, one must have a large number of particles in each debye volume. So that's goes by a name plasma parameter. In some books, this is defined as 1 over nd, what I call here 1 over nd. So if you determine the number of particles in a debye volume, it goes as the electron number density, lambda d to the cube. I always put this somewhat approximate symbol because these are all estimates, and one can always do better. But for illustrative purposes, it's enough that you know the basic concept, and one can always generalize it. Given the ion inertia is large, it is not so moving so much, and that's why the contribution to the current comes mainly from the electron motion, okay? Because they are the ones that are moving fast and fast. Similarly, so this is one scale. In plasma, you have many scales, and unless all these scales, over and above all that mean free path and everything that we discussed, that is still obeyed, that the density be dilute enough that the quantum effects are negligible and stuff. So all that is still applicable. Over and above, you have some more scales like the Debye length scale and the plasma frequency. What is a plasma frequency? If I take a plus here, and suppose by accident, I simply create a charge imbalance, plus and minus charges are separated. That means there will be a net charge density. It has to die out. Okay? It has to die out. But how will it die out? The plus will attract the negative. It will come towards it, but then it will overshoot, will go on the other side. It will again be brought back. So the electron will essentially oscillate with this frequency omega p around a positive charge. And this oscillations typically is very, very fast. Okay. For high conducting plasma, this oscillation is very fast. Okay. So what it does is that if you are looking at time scales that are very close to the plasma frequency, or at frequency that is even higher than the plasma frequency, you will then be sensitive to this plasma oscillation. In a way, you are essentially also sensitive to the charge separation. At those time scales, the charges are separated. But suppose you are interested in a slow dynamics, like for the dynamics on the order of the galactic evolution time scale or the solar evolution time scale, this plasma frequency turns out to be on the order of a few seconds, whereas you are interested in the dynamics over years, yeah, hundreds of years or millions of years. So in that case, over those slow time scales, the plasma frequency can be, this effect of charge imbalance can be ignored. So that's another criteria to defining the space plasmas or the fluid plasma. So I'll just draw it or sketch this part here, that one could study plasma in a particle picture, a fluid picture. Actually, there's more picture, but I'll just highlight these two. One can have a kinetic picture, for example, yeah, somewhere in between. And one just has to be lucky that one can deal with this in terms of fluid. Okay. And as I said, it's not necessarily possible all the time. The charges in, say, the pulsar's magnetic fields, that you would rather like to study in terms of the orbit theory compared to the fluid picture. The motion of cosmic rays or the charged particles trapped in magnetic field leading to the synchrotron radiation. These are a few examples where individual charged particles or various charged particles are trapped in a magnetic field that this is not, that particular individual charged particle is not controlling that electromagnetic field. So field and particles are thus separated. Field is externally supplied and particles are essentially trapped in those externally supplied magnetic fields. So that's a different picture. But here we are talking about a collective picture when things are too tightly coupled. So if induced fields are significant, the orbit approach is often not suitable for studying the dynamics. Okay. Induced fields meaning the charged particles are after all in motion and they can induce the electromagnetic field. And if that field is significant for your study, that you will decide for your own purpose, then you are basically talking about some coupled system and rather look at the self-consistent response of fields on the sources and source on the fields. And if typical length and time scales of interest are such that the time scales of interest is much larger than the inverse plasma frequency, yeah, so it's basically dealing with slow dynamics, and the length scale that is much larger than the Debye length. The Debye length typically is even smaller than the mean free path. Okay. So if the system, and this is like the typical scale or the system scale, you can say, is much larger than the Debye length. If these conditions are obeyed, then the charge separation can be ignored and fluid light description becomes possible. So we are mostly dealing with this situation here. Okay. All right. So because there was a question yesterday about how do we measure the Reynolds numbers on the sun, or how do we know that the Reynolds number of the sun or the astrophysical objects are very large? How is it determined? So that is a valid question, and it needed some introduction to plasma physics. After all, even in those medium, these microscopic transport coefficients, that's another name for, say, conductivity, resistivity, viscosity. You can put them all in one word, microscopic transport coefficients. Okay. And they lead to dissipation, like the resistivity and viscosity. So how do you know for sure that our estimates are right, and how do you even begin making any estimate of that? So then essentially this is all driven by collisions. After all, when you have heated a plasma, you might think that with larger temperature the collisions will increase, so the dissipation must also increase with temperature, right? Isn't it? So that is true, and I think I made a mistake here, and I'm very sorry for that. Please note this is plus here and minus here, okay? Because that's exactly what I wanted to say, and I see that there is sign error here. Sorry for that. The reason is simple, because with temperature, while you might expect that the resistance is increasing, which is true for viscosity, for resistivity it is not the case, right? Because with larger temperature, you are generating more and more number of ions, and so conductivity is increasing with temperature. So resistance is essentially dropping with temperature. Okay. So that's why this is a minus sign. Sorry about that, but please note this is minus here, and this should be plus here. Okay. And please check that also, yeah, that it is right. But I think this is just plus here and minus here. Okay. So how do you determine this conductivity? You appeal to some model. Ohm's law is simply a model that relates how much current a system will have for a given imposed electric field, and conductivity sigma, electrical conductivity sigma, is simply a proportionality constant. It's Ohm's law, right? J is equal sigma E. So how do you determine that? So this estimate, this is also known as Spitzer estimate. So this is based on the electron ion collisions here. Okay. Ions you can pretty much consider as fixed. Electrons are going and colliding with them. So if you work out the mean free time between each collision between electron and ion, so within that time, for that time tau e, the electrons are accelerated under this electric field E. Yeah. And you can work out what is the so-called terminal relative velocity of electrons with respect to ions. You can work out that terminal relative velocity. Okay. That is your current density is then written in terms of that relative terminal velocity, through which you can work out your collision cross section. After all, an electron is going and hitting an ion which is posing some sort of an area. So that cross section gives you a collision cross section. There is a collision time here, through which you can work out all the relevant quantities and put it for J and E. Whatever you get as a proportionality constant is basically sigma. Yeah. And given that these are all random motions, so the way you will go is that you will equate energies that are mv square, mass of electron, times the velocity of a square, velocity square of for the electron is equal to the Boltzmann constant times temperature on an average. So it's all average description going on. So you equate mv square to the kBT, that's where the temperature comes, and you determine the mean free time for electrons. You determine the terminal velocity for electron. That basically gives you the J, isn't it? J is equal to number density times the charge times the velocity field, and EV. And then you appeal to the electrostatic interaction, which is energy that electron has must overcome, or must, for a strong interaction, that it comes very close to the ion. So the electrostatic potential, energy Z E square divided by the impact parameter B. So if you do all that, you'll find that it is not that hard to get to an expression where the sigma turns out to be positive 3/2. So it basically increases with temperature, which is also what you expect. You increase the temperature, more number of ions are present. That will lead to the larger and larger conductivity in the medium. Okay. So the microscopic resistivity is defined as c square by 4 pi sigma in the Celsius unit. That becomes T to the minus 3/2. Okay. Similarly, for viscosity, viscosity is a dissipative term for the momentum transport. So while electrons are important for electrical conduction, for momentum transport, much of the momentum is transported by the ions. Okay. So the kinematic viscosity, please also note that this is a kinematic viscosity, and not this dynamic viscosity, eta. So eta was previously defined also as dynamic viscosity, but from now on the eta is resistivity of the plasma. It's a microscopic resistivity of the plasma. So this viscosity one can work out based on the ionic transport. You work out the thermal motion of ions, you work out the mean free path of the ion. The nu has a dimension of length square divided by time. So it's some sort of a velocity field multiplied to the mean free path L. Again, you take the strong collisions between ions now. So earlier it was ZE square. This time it will be Z square E square. One important fact about the eta was that it was independent of electron number density. For viscosity, you find that this is the dependency. So that increases with temperature. Okay. So in your plasma, whichever species contributes most to the momentum transport, you involve that species to derive your viscosity. For current flow, whichever species is involved maximally for the electrical conduction, you take those parameters or parameters of those quantities to define or to derive the expression for conduction properties like sigma and eta. So you roughly know that this can be derived, and for any system, for a given temperature, you can work out what these numbers should look like. And if you put it together for the Reynolds number expression that I showed before, you find that these numbers in astrophysics are typically very large. That means the dissipative processes are very small. Large Reynolds number, meaning you are balancing the inertial terms with the dissipative terms, and the inertial terms, that means, are much more dominant. Okay, so having said all that about plasma, fluid, and how to define and various things, you then come to the Maxwell's equation, because ultimately these are the equations that are governing the various sources and their impact in terms of the electromagnetic field. Okay, so we'll be using CGS units, and now we are slowly drifting towards magnetohydrodynamics, single fluid. So you write down your equations for B and E, the time evolution equation, the curl equations and the divergence equations. You know the divergence B is 0. Divergence of E here has been written as 4 pi rho E, but I've argued already that this charge density rho must be 0, right? It's a quasi-neutral plasma. So in a quasi-neutral plasma, the charge density must be 0. There is no charge density. Okay, because as soon as there is a charge density, it will be shorted out by the conductivity of the medium. There is another term which is a displacement current term, yeah. And we will see what happens to this for astrophysical examples. So you have these equations. I already argued that the electric fields, if generated or if produced in a plasma rest frame, they will simply be shorted out. And that is one reason that we talk of magnetic fields in the universe and not the electric fields in the universe. Because electric fields are essentially on large time scales, basically 0, because they are shorted out due to high conductivity. But magnetic fields, once created, it is very hard to get rid of them. That's why there's a talk of magnetic fields. You can go to fixed frame of reference and write down your Ohm's law, and it turns out that this is again a proportionality constant sigma, exactly the same thing as we saw before here. J is sigma E plus phi cross B by C. Okay. Yeah. You can already see that if you take a large conductivity sigma, you take it on the other side. So J by sigma, yeah, J by sigma can go to 0 for high conductivity plasma. So electric field is of the order of V by C times P. Okay, so it's already V by C factor is small. We are dealing with cases when velocity field is much, much smaller than the speed of light. Okay, this C is speed of light. So you can use this expression here and eliminate J, define resistivity exactly as this formula, and you simply write down this equation here. Okay. So what you find is that there are these many terms, and this particular term, it's an equation for electric field. So that means the dimensions of time here must be same as dimensions of eta by c square. And if you work out how much it is for the space plasmas, for fully ionized plasma, it's also known as Faraday time scale. And you can, there are many ways to derive this, by the way. You could start from here, the continuity equations for charge density. That means you will write del rho E by del T is equal to minus divergence of J. Okay. This has the same form as we saw for the continuity equations for mass conservation, except here it is the charge density, but the expressions are identical. The conservation laws are in that sense very powerful. You write the del del T of rho E. It can only change through fluxes. So you write down is equal to minus divergence of J, which is basically charge flux. Charge flux gives you current. And Then you write in the plasma frame J equals sigma E. So divergence of sigma E gives you sigma divergence E. Then you replace divergence E in terms of 4 pi rho E. So you get exactly del rho by del T is equal to minus 4 pi sigma rho E. Okay, it's an exponential drop, right? Del rho by del T is equal to some minus constant times rho E. You can solve it, and you again exactly get this time scale for the dissipation of the charge imbalance. So del rho E by del T will offer you a solution for rho E, which will decay away in a time which is on the order of 10 to the minus 14 seconds for ionized plasma. Okay. So you see here it's written correctly that eta is going as t to the minus 3 half, unlike what I wrote here. So this is again, yeah, this must be minus, so please note again. So this is also known as a Faraday time scale. So you see for a space plasma, this number is giving you 10 to minus 14 seconds. And if you are interested on time scales that are, so this time is basically the time scale of interest. So if those time scales of interest are say years or millions of years, so 10 to the minus 14 divided by so many years in terms of second, this term is essentially zero. Okay. So the displacement current term is ignored in the usual MHD simply because it is so small, because the resistivities are very, very small due to large conductivity. And therefore, you can write down this electric field in terms of the curl B, V cross B by C. So you see that this is somewhat special, that normally if you take a non-relativistic limit of a relativistic system, you will say that the terms of order V by C are thrown. In electrodynamics, you cannot do that. Yeah? You will throw away basically all the effect, because in one frame, what is electric field, in the other frame, it can be a magnetic field. Right? So it's a frame dependent thing. And in order to keep the essential physics in control, you must, even in the non-relativistic limit, must keep the terms of order V by C, and only terms of order V square by C square are thrown. So it's somewhat special and unusual. Okay. So if you do that, do write electric field in terms of this quantity. Now you have this induction equation. Del B by del T is minus curl of E. You just substitute for E here, and you have an evolution equation for magnetic field. Okay. You can do that, and you find what is famously known as an induction equation. Okay. So this is all derived from the Maxwell's equation of motion. You don't need too much. This velocity is now again like to a fluid element we had assigned a smooth velocity field. To a plasma element now you assign this plasma velocity field, not to individual charged particles. It's good enough. So magnetic field will evolve according to this equation, where eta is your resistivity, microscopic resistivity of the plasma. If that is uniform, you can pull it out and you solve for curl B, appeal to divergence B being 0, you get an equation which is somewhat simpler. So you can see that you have seen this equation before, right? If I were to forget about this term for now, we saw that, let me go back to show you that we had discussed this. Oh, okay. Maybe I didn't write it there. The equations for, oh yeah, here. Look at here. So the vorticity evolved exactly in the same form. Del T of omega or B is exactly equal to curl of V cross omega or curl of V cross B. Okay. What was the consequence of this for an ideal case when there was no dissipation? Is that the circulation or the vorticity was frozen to the fluid. Similarly, because the mathematical form of the equation is same, one will derive that the magnetic field is also frozen to the plasma for the case when eta is 0. Okay. But again, note that eta equal to 0 and eta tending to 0 are two completely different things. And while some people immediately draw this conclusion that for astrophysics, eta is so small that you can throw away, one must be very careful. So I'll summarize these comments. I don't know if how much time I have. Let me see. Okay, so I think I'll go a little fast. MHD is basically a non-relativistic limit of Maxwell's equation. Plasma is usually modeled as a single fluid, which is highly conducting. If you work out the Lorentz force, whenever you have a magnetic field and electric field through sources, the sources are J and rho are the sources, and the induced fields are E and B. These are all coupled. This can lead to this, and this can influence that. So in that sense, it's all coupled. So these electromagnetic field will also exert force in the momentum equation. So you remember the momentum equation in fluid was written down without this J cross beta. J cross B is your Lorentz force. And you see that I have not written down an electric field here. And you can work it out yourself. It's an easy enough calculation that the electric part of the force, after all, for a single charge, what will you write as force? QE, yeah, plus J cross B, yeah, for a single thing. So if you take a ratio of this term divided by this term, you will find that this is of order V square by C square. That's why the electric part of the force is 0 in this non-relativistic limit. So Lorentz force can be directly added to the right hand side of the momentum equation. Okay. So it was a Lorentz force density, yeah, because all these number densities are involved. So it's a Lorentz force density, and you divide by rho, so it becomes Lorentz force per unit mass, this quantity. Okay. So electric part is therefore not considered, and electric fields are shorted out. So it's also not part of discussion, mostly in astrophysical plasmas. You can immediately see that if you take a limit eta going to 0 in reduction equation, that becomes a flux freezing case. I'll write down once again, and we'll show one simple consequence of that. But this is something that you've already seen in terms of Kelvin circulation theorem, that this form of equation without this is such that if you write the B dot dA or B dot ds and take the entire area integral, the d by dt, the convective derivative of that, is 0. So the magnetic field through an area, or in other words, the flux, is frozen to the plasma. So you take the plasma, you D-shape it, you take it wherever, the plasma, the magnetic field will move with the plasma element. If there was no velocity field, you see, there was no velocity field, then this was a diffusion equation. And then the plasma will decay. Okay. You can work out that if eta is very small, the decay time scale is very, very large. Okay. So decay time scale will go as 1 over eta, right? Yeah. Some length scale square divided by eta is your rough decay time. So if you work out the eta for a galaxy and you determine the microscopic decay time of the magnetic field, you'll find that the magnetic field, if there was a magnetic field in a galaxy, the decay time scale determined from that eta is on the order of age of the universe, or much larger than the age of the universe. And one can argue that the eta is so small that magnetic field need not be supported, and they will always exist if they had existed once. Okay. You remember that in Kelvin circulation theorem discussion, we had considered a barotropic fluid. So that means the gradient P cross gradient rho term was 0. So that would be a seed term, and similar will happen here also. but for a barotropic fluid, that will be 0. And there was a time in the early universe when that term need not have been 0, and that would be the origin of a seed magnetic field or the first magnetic fields. You see that this equation cannot give you the first magnetic fields. If the universe started with B equals 0, this equation cannot give you any magnetic field, because the B equals 0 is a valid solution of this equation. So the magnetic field in the first seed magnetic field must come from other sources. So it's a battery term. Okay. But given the plasma or the medium in the universe, they are highly turbulent, you get corrections to these diffusion quantities, and you find that the turbulence will lead to much faster decay of the magnetic field. And unless supported by some sort of a dynamo, one cannot maintain or observe a magnetic field. So this remains an active area of research today, that what is essentially driving all these magnetic fields in different scales. A consensus is that it is a dynamo process where you dump the kinetic energy from the plasma particles. You convert that kinetic energy into the magnetic energy, which you call a dynamo, in order to maintain and generate these magnetic fields in the universe and different astrophysical objects. Okay. You can always have a magnetic field, by the way, by having a current. So imagine I have a current carrying wire like this. Yeah. So that will always give me a magnetic field in the center, right? That is not allowed for dynamo. It must be self-consistent generation of magnetic field through the motion within the plasma, through the motion within the system. So one can always put the entire sun into a magnetic field or a current that might give you a magnetic field on the sun. But when we say solar magnetic field, what we mean is that this is all internally driven. Motions in the sun, they are driving this magnetic field. Okay, and that dynamo is basically driven by this flow V. There are again conserved quantities are of great interest because they constrain the dynamics in such a way that you can make useful predictions in order to test various theories. One interesting invariant of the problem is magnetic helicity. Yeah. You know that divergence of B is 0. That means the magnetic field can be expressed in terms of a vector potential. So B can be written as curl of A. So any quantity whose divergence is 0 can be expressed in terms of a vector potential. So B can be written as curl of A. So divergence of curl of A is always 0. Then you can construct this quantity, and I will not have time to fully discuss this. But the magnetic helicity defined by a volume integral of A dot B evolves according to this equation. And given eta is essentially close to 0 for astrophysical case, it doesn't evolve much in the astrophysical context. So dH by dt is nearly 0. Okay. So it's very interesting that even when events like magnetic reconnection happen, when you have a solar flare, right? You can have event like solar flare, or you might expect that the helicity might change. The evolution happens in such a way that the magnetic helicity remains conserved. It is essentially taking two different magnetic field lines, cutting them and pasting them, because reconnection is exactly doing that. It's taking the different field lines and making new connections in the field configurations through these reconnection events. It turns out that this is very nearly conserved for even high magnetic Reynolds number system. Magnetic Reynolds number is basically ratio of this by that. And like fluid Reynolds number was some typical L velocity divided by nu, Reynolds number, magnetic Reynolds number is LV divided by eta. Okay. For astrophysical cases, both fluid and magnetic Reynolds numbers are very large. Okay, so in other words, these terms are very, very small, but they can be important. Okay. And there are some predictions which I will not have time to get into, that they can lead to predictions in terms of being effective tracer of the origin of magnetic field. Remember that we are still discussing a lot about the origin of magnetic field, and there are clear predictions in terms of bihelicity of magnetic fields if they are produced by certain dynamo type effects, and these are testable, and one is routinely testing this. Just as a quick application of flux freezing, which I will not derive, you can look up any textbook. The statement is such that the convective derivative of a magnetic field through an area is basically zero. So what it means is that I can take a star, suppose it's a sun-like star. It has a magnetic field of say 1 Gauss. It has a radius say of 10 to the 6 kilometer. So the flux of the magnetic field through the sun, through the star, is B1R1 square, right? 4 pi R1 square is the area. Magnetic field we multiply. So that's the flux going out from the star. That is a conserved quantity. So if that were to collapse, and you can just take an extreme limit, it's not that it has to be exactly like that. It's just an illustrative example. Suppose you were to collapse it to a neutron star scale from 10 to the 6 kilometer to 10 to the 10 kilometer. So 10 kilometer. So the magnetic field given this B1 R1 square must be equal to B2 R2 square. You can work out how much magnetic field you will just gain just by this idea of flux freezing. Given that the field is frozen, 1 Gauss will become 10 to the 10 Gauss. It's not very far from the strongest magnetic fields you know, right? Some of these ideas are definitely working, and there are good enough evidence that these are the regions for uh, enhancement of the magnetic energies. But at some point, you will also notice that this is not enough, and you need more and more magnetic field in order to explain the observed phenomenon. And that's when the dynamo comes in, and that fundamentally relies on the eta term, the small eta, but the magnetic configuration must change, and that is only allowed by having finite eta. When you ignored eta, or when you didn't have eta equals 0, that also meant that the magnetic configuration cannot change. So if you have a field topology of some form, you can do whatever with these. You can take them from one place to another. You can do twist them, turn them, but this field topology remains invariant so long as eta is 0. But in order to generate a magnetic field, at some level, you must fundamentally change the field configuration, and that relies on having a finite eta, microscopic eta. So I think I'm done with this macroscopic plasma part, and we'll be happy to take questions.
Okay, so there are a few questions. Just give me 1 second. Okay, so let me take one question from Vaibhavi Gavas. His mic is not working. She has asked two. I will take the first one first, and then if we have time, we'll take the second one. So first is, on what observational basis is the mapping of galactic magnetic fields done?
On what?
Observational basis is the mapping of galactic magnetic fields. And I guess what she's asking is, what are the observations used to map galactic magnetic fields?
Yeah, okay. So these are basically various different observations combined, and simplest is to look at the synchrotron observations, which that's why it does not give you any arrow on these lines, but it still gives you some sort of a coherent picture of the magnetic field. So yeah, these are essentially from synchrotron or rotation measure observations. Yeah.
Okay, so the other people who asked questions, can you please raise your hands? So Amit Tanwar, can you raise your hand so I can see you? Amit Tanwar is not around. Okay, Love Preet. Yeah, okay. So, Lovepreet, you can ask your question.
Hello.
Yes.
Good afternoon, sir.
Yeah.
Sir, how we can relate the Reynolds number to plasma?
Reynolds number to plasma.
Yeah, sir.
So you think of, say, now that there is a picture of galaxy on the screen. So let's look at galaxy. So you can look at typical velocities, and these are to do with turbulent velocities. So in the galaxies, one believes that much of the turbulent motions are driven because of supernova explosions. So you can go to those scales and work out what on average is the typical velocity in a galaxy, and at a scale which is roughly, say, the thickness of the disk half thickness. That roughly is the, suppose, the scale you are interested in. So that might be say half a kiloparsec or a few hundred parsec, and then you work out the typical velocities that are essentially driven there from the supernova explosions, and then you work out these numbers that I showed in terms of eta and nu, exactly because you know these uh, temperatures in the plasma, and so you can immediately determine what is the resistivity and viscosity in the medium, and then you plug in these numbers for the Reynolds number formula. Reynolds number is a useful description. As I said, this is perhaps one of the earliest and strongest statement about the fluid dynamics, that it does not depend on multiple parameters, because naively one might have thought that it depends on the length, depends on the velocity, depends on the resistivity separately. But it turns out that there are control parameters that reduce your number of parameters in the problem, which is a great simplification. In fact, it's a great insight. And that's why the Reynolds numbers are very important. And then you just put in these numbers, L, V, and nu or eta. If it is eta, it becomes Rm, magnetic Reynolds number. In fact, there's another parameter, Prandtl number, magnetic Prandtl number, which is Rm divided by Re. So as you see that this is simply balancing the term, which is dissipative term, with an inertial term. And this is to give you a measure of what is the main driver for the dynamics. So in that sense, it's very useful. So one can always measure it, and turns out that the microscopic dissipative terms for astrophysical objects turns out to be extremely small. Yeah.
Okay, so I'm unmuting Amit Tanwar. There's some problem with raising hands, but I found him. So go ahead, please.
Hello, sir. My question is related with the induction equation.
Yes.
In induction equation, when n is 0, I agree that magnetic field is frozen.
Yes.
But that equation speaks about the time evolution of B. So how B changes with time? What are the ways by which magnetic field can change or evolve with time?
Yeah, so as you see from the equation that suppose you forget about the velocity term first, maybe simpler. Then if you start with some magnetic field, you can have a magnetic field which you are not supporting. Suppose just a magnetic field in a wire, even, for example. Yeah, it has some sort of a resistivity. All it can do is decay. So the solution will look like an exponential minus eta wave number is square time. Okay. So you can write down the diffusion solution for this diffusion equation without the V term. So field will only decay. Now, depending on what type of velocity field you have, the magnetic field will evolve according to that velocity field. Okay. Note that the velocity field is also affected by the same magnetic field in terms of this equation here. But suppose you start from a very weak magnetic field and you ignore this term here, or you can take even drastic approach, which is pretty much done in most simple dynamo models, that the velocity is given to you. It's a kinematic approach. So velocity is given and you work out how the magnetic field will evolve. Suppose you forget about eta. So it turns out that given the magnetic field is a pseudo vector, in order to generate a magnetic field, you must also break the symmetry of the flow. So ordinary flows cannot generate the magnetic field. There are many anti-dynamo theorems that you might want to look at.
Okay.
And it turns out that one of the simplest way to generate a magnetic field is by having a flow which is helical. So if you take a flow V, dot it with a curl of V, so V dot vorticity omega, if that turns out to be non-zero on an average, then you will say that it is a good enough a flow to generate a magnetic field. It also goes by a name alpha effect.
Okay, sir. Okay. Thank you, sir.
And I just wanted to add that given this linearity of the equation, it evolves typically as an exponential. So if it becomes unstable, it grows exponentially. So it's also a sign of instability, that it must be exponential. It decays exponentially, it grows exponentially. And that comes from just the linearity of the equation.
Okay, so there is one question that Desh has selected on the YouTube chat. So if you can look at it.
Yeah. So there's a question: as the plasma will cool down over time, it should simply become gas. Since sun also constantly gives out plasma wind, so there would have been gas between sun and other planets. Okay, I perhaps don't fully understand what is the question, what exactly is meant by that, but
They're asking, should there be some plasma or gas in the solar system between the sun?
yeah. So I think I said that if you go to any medium, interplanetary medium included, you don't need to have a fully ionized medium for it to become a plasma. A partially ionized plasma is good enough because the conductivity essentially approaches to its maximum value already when the ionization fraction is close to about 1%. So it's a remarkable thing to note that you can have a plasma which is pretty much neutral, and only 1% of the plasma becomes ionized. After all, it is a function of temperature, yeah, and it's a function of various things. And so in the interplanetary medium, it's not as if like the whole plasma must be fully ionized. Suppose there is a good enough neutral fraction, it is still okay, because the medium still becomes electrically conducting. As far as it is electrically conducting, and one is able to define all these criteria in terms of Debye shielding and plasma parameter, it is good enough to deal in terms of plasma as a fluid. It's not always true that this is the only correct description. There are various departures known. If you look up the solar wind, there are enough hints that one must, or the fluid description is not adequate. Then one tries to do the kinetic description of plasma, also in the solar wind case. So yes, depending on the situation, and plasma, of course, becomes much more complicated. Even in the reconnection events, at some scale, the fluid description breaks down. After all, when eta is very small, your typical length scale involved because of through diffusion is also very small. And if you are looking at events at sub-diffusion scales, your fluid description is not adequate. And a lot of people actually try to look at particle in cell type picture, again going all the way up to the particle picture, in order to fully understand the reconnection or even even the origin of the resistivity and these things. These are very much affected. So in plasma, of course, you have all range of. It's only for some slow dynamics, smooth dynamics, that this is good enough. But if you ask a question in much detail, one has to, of course, to be much more careful. Yeah.
Okay, I think there are no other questions worth answering, so we can stop.